All right, chapter 13 again, exponential and logarithmic functions. This time we're in section 13.2 on logarithmic functions. So last time we looked at exponential, this time we're going to the logarithmic. All right, so here the inverse function of exponential functions are logarithmic functions. So that means if we take f of g, which we've done before, of x, that's equal to x. And so basically we're plugging in the g into f, and we end up with getting x out. So it's an inverse function. Now logarithmic function is denoted by, y equals log base a of x. And this is equivalent to x equals a to the y, where a has to be greater than 0, but it cannot equal 1. And again, here a is going to be our base, y is going to be the exponent, and x is going to be the value. And what happens is we're going to see two different forms. We're going to say, well, this one is our logarithmic form. And then guess what? We're back to exponential form. So we have the exponential form and the logarithmic form. So when I was saying last time, if we didn't end up with the same bases and we could set the two exponents equal, well, what we could do is we could take logs. And so this is kind of how we would be converting between logs and exponents. And so it's easy to convert between them. So if we have the log function, what we do is we start with the base and we'll say a raised to the power y is equal to the x, and that's a to the y equals x, and that's how we got this one too. We took a, raised it to the power y, and that equals x, okay? And so that's how we're going to kind of convert from log to the exponential. And if we go from exponential to log, then we just have to kind of think about, well, which one is the exponent, which one's the base, which one's the value, and then we just plug it back into our log function, and then we can get that back out. So we're going to evaluate logarithmic functions, and this really requires us converting between logarithmic and exponential forms to be able to create the equation that we can solve by hand. So let's start first by converting a few of these. And so we're going to start with going from log to exponential, and then we'll go from exponential to log. And so remember, it's going to be this value raised to that, and that's going to be equal to that. So we're going to say 3 to the x is equal to 4. Okay, and that's all they want us to do. Just change it to the exponential form, which is this. Okay, so we're going to do the same thing here. We're going to take our base, raise it to the power 7, and then that's going to equal that. So we're going to take 3 to the 7 is equal to x. Okay, so base, and then that's the value, and then that's our exponent. Okay. All right, so what do we have here? 7 to the 5th equals z. Well, what is our base? Our base is 7. Okay, so that's just our base. And that comes from here. Okay, now our value is here z on this one. So value is z. So we have that. And our exponent is 5. So we're just writing it down what we have. And so what we're going to do is we're going to go backwards. So we're going to say log base 7 of z is equal to 5. And if we go backwards, that's 7 to the 5th equals z. And that's what we have there. So, writing it out this way makes it so we can get to this form. And this form going backwards to the exponential is quicker because we know it's just that raised to that power is equal to that. So what about this one? Okay, well, our base here is going to be m. Okay, our value is going to be 5. And our exponent is 3. So when we write this again, that's log base m of 5, that's equal to 3. So m to the 3rd equals 5. And that's what we have here. Okay. So now they want us to take and find the exact values for these. All right, so how do we find the exact value? Well, sometimes what you have to do is you actually have to simplify, and we're going to just say, well, that let's say is equal to x, because that's what we want to do. We want to solve this, so we're going to give it some variable value. And then we just take and say, okay, well, we'll take our base to that value is equal to that. So we're going to take 343 to the x equals 1 over 7. So we just used our conversion from logs to exponents to help us here. Now, what is 343? Well, 343, it's going to be a factor of 7, I'm betting, because this is 7 to the negative 1. And so I'm going to want 7 on this side. And so 7 times 7 is going to be 49, times 3 is going to be our 343. So that's going to be to the 3 and then times x. Now we can set those equal. 3x equals negative 1, divide by 3. X equals negative 1/3. Okay, and so we've just solved this logarithm, using exponential way to solve it like we did in the first section of this. We got to the basis, set the exponents equal, and solve for x. And we're going to do the same thing here. We're going to say, well, that's equal to x. So now we're going to take 6 to the x is equal to 36. Well, remember 36 is 6 squared, so we have 6 to the x equals 6 squared. And so this one's really simple. We just have x equals 2 because we have like bases. So we set the exponents equal, and we have that one solved directly. So this one, first one was a little harder. We had to know that that was a factor of 7, and the clue was what this value here was, and so they're going to make it so it's pretty easy to go through and simplify like that. Okay. All right, so let's go to the next one. So the next one we're going to do is going to be similar, and we're just going to say, well, that equals x. And so we take 5 to the x equals 125. Well, what is 125? Well, that's 5 times 5 times 5. So that's 5 cubed equals 5 to the x. Bases are the same, set their exponents equal, and we get x to the x equals 3. Okay. All right. What about the next one? Well, I'm going to do the same thing. I'm just going to say, well, that equals x. I'm going to take base to the x, so 4 to the x equals 1 over 64. All right, so here at this point, we have to convert. So 64 is going to be 2 to the 6th, but it's in the denominator, and if I want it in the numerator, that becomes 2 to the negative 6. Well, 4 is 2 times 2, so that's 2 squared times raised to the power x, so that's 2 to the 2x. Now I've got like bases, so I can say, well, 2x equals negative 6, divided by 2, x equals negative 3 over 2. Okay, oh wait, 3 over 2, it's equal to negative 3. I don't know why I wrote that 2 still on there. Let's just rewrite that again. All right, 6 divided by 2 is 3, and then I don't know why I saw 2 again, so I'll put it again. So x equals the negative 3, or yeah, negative 3, okay? All right, so that's how we're going to solve things when they have it given like that. We're going to set it equal to x, and then we're going to use our exponential way of solving things. Now with the domain, we have to sometimes find the domain. So the domain of a standard logarithmic function f of x equals log base a of x. Well, the value of the logarithm x, basically in this case, whatever that value is always positive because we can't take a log of a negative. Hence, the domain is going to be from 0 to positive infinity. Now, when we start adding and subtracting things in here, so, say we have log base a of 2x plus 4, things like that, that's going to start affecting what our domain is, but initially it's that 0 to infinity. So what happens if we don't have that? Well, what we're going to do is find the domain of any logarithmic function. And what we do is we identify the value of the logarithm. So basically whatever's in parentheses or whatever that x value is, it's going to vary depending on the problem. We're going to set whatever it is. So, like that 2x plus 4, we're going to set that greater than 0. So we're going to set that 2x plus 4 greater than 0. We're going to solve this, and so if we solve that, we're going to take 4 to the other side, so we're going to get 2x is greater than negative 4, and when we get that and divide by 2, x is greater than negative 2. Okay, so that's solving that inequality. And then it says rewrite the inequality in interval notation. Well, we want any value for x greater than negative 2, not greater than equal to, so we have a parenthesis, so negative 2 to positive infinity, and that would be our new domain. Okay, and that's the domain for when we have log base a of 2x plus 4 instead of just plain old x. Okay, if we've done the plain old x, remember that's just going to say x is greater than 0, and we get the 0 to infinity on that one. Okay, so we're just setting whatever the value is greater than 0, solving, and then writing it in interval notation. All right, so let's do a few of these. So again, pretty close to what we just did on the last one. Here we're going to set the value, which is this, 3x plus 7, greater than 0. So we'll subtract 7. 3x is greater than negative 7. Divide by 3. X is greater than negative 7 over 3. So we're going to go from negative 7 over 3 to infinity, and that would be our domain. Okay, and so you could say domain, and that's equal to, or you can just put the D for domain, or you just write the interval if that's all they ask for. Well, what about this one? We have 4 minus 8x is greater than 0. And again, we don't care what base it is, because what we're really worried about is that domain, and it's just that value function. So now I'm going to take the 8 over here. So I'm going to add 8x. And so 4 is greater than 8x. So divide by 8, and that's equal to 1/2 is greater than x. And on these, you always start with the variable part and read whichever direction it shows. So here we're saying x is less than 1/2. Well, x being less than 1/2 means it's going to this direction. Here's going to be our 1/2, and it's going to be less than that, so it's going that direction. And so we're going to go from negative infinity up to 1/2, and then a parenthesis that way. So you always have to be sure to change, read it from left to right. Or what we could have done is we could have added 4 to the other side, and so negative 8x is greater than negative 4. And then we divide by negative 8. Now when you divide by negative, you have to switch your sign, and so that's x is less than 1/2. And so that way we usually read it properly. When it's this way, people have a tendency to read it as x is greater than 1/2 instead of x is less than 1/2 properly. Okay, so that's a key. So it could do it both ways, and both of them say the same thing, that x is less than 1/2. All right, so we have not only plain logs, common logs, we also have things called natural logs. And natural logs are defined by the following. What we have is we have a base e. Okay, so a log base e of x is going to be our natural log, and most of the time we rewrite that as just ln of x. So instead of putting log base e of x, we write ln of x for short, and you'll see that on your calculator. So it's the natural log there, and so this is true if and only if x is equal to e to the y, and that's going e to the y equals x, and that's going back to converting from logs to the exponential form. And the base e is basically just your irrational number, which is Euler's constant, which is about 2.7182181, and so on. So it's built into calculator, so we really don't have to remember what all that is, but that's what the Euler's constant is equal to. Okay, now the common log, that's what we're most of the time used to. It's log base 10 of x, and we just shorten that to log of x. Okay, and again, that's also in your calculator, so we just have that function, and we can use it no matter what. And it's kind of nice how that works, as far as both the log and common log are available on your calculator. And here the base is 10, and basically, like I said, it's just left off. And here you have your 10 to the y is equal to x, and that's the exponential form for the log form. Now, when we graph logarithmic functions, as with other types of graphs, what we're going to do is we're going to plot points. Granted, we can go ahead and we can do the normal, plug it in the calculator, it spits it out, but a lot of times they're going to say, what is the points, list 2 or 3 points, and they'll ask you to actually figure out what they are. And so the basic logarithmic function, before there's any transformations, will not cross the y-axis. Only when we have those transformations in there that it's going to cross the y-axis. So our properties of the basic log function are: the domain is going to be all real numbers greater than 0. So 0 to infinity. When we looked at those others, if we add the 2x plus 4 inside of the log function, so we'll do log base 10, then we had a different domain. But the plain basic one is 0 to infinity. There are no y-intercepts, it never hits the y-axis, and the x-intercept is 1, 0. And if a is greater than 1, then the function is increasing, but if it's between 0 and 1, it's decreasing. So those are kind of the key things there. And so let's kind of see what we have here for plotting. Now, with these logs and things like that, sometimes it's kind of difficult. Now, remember here, x is going to be greater than 0. So if we set that value, we know our domain is going to be all the values to the right. So do we have to plug in any negative numbers? No, it's always going to be positive numbers. Okay. Now, how are we going to plug this in? Well, the key way to do this is to, again, plug points in and then simplify from there. And so what we have is, remember, it's going to be 1/4 to the y is equal to x. Okay. And so sometimes it makes it so it's easier to plug in our f of x value and simplify. We're just going to take and plug in numbers here and then get out the x value. And sometimes it's easier to plug in x values and get out our y values. But, maybe we should go ahead and plug in our x values. We're just going to kind of go across here. And I don't know, let's do let's do this one. Let's go here. Let's plug in 1. Let's go half of that because we want to see what it gets too close to that y-axis. So maybe let's do a half. Let's do, y equals 0 because that's going to be 1 there. What about -1/2 for y? So it's going to go down below now. Let's go up to a -1, and I don't know what we'll do something different. We'll figure out something. But I think that's enough here because that'll get us up and down on both sides of our x-axis, and we should be able to get a decent point here. So if we plug in 1 here, 1/4 to the 1 is 1/4. Now to the half, so 1/4 to the half, that's going to actually make it so we get the square root of that. And so the square root of 1 is 1, square root of 4 is 2, so that's going to give us 1/2. Now anything to the 0 is 1. Now what about this? Well, we're going to take the square root of that, and so that's going to be 1, actually it's to the -1/2, so it's going to be 1/4 to the -1/2, so that's going to give us 4/1 squared, and or square root still, sorry, and so that's going to be 2/1. So that's going to be a 2. And if we plug in -1, we just flip that over. That's going to give us the 4. Okay. And again, that should be enough, I think. We don't need that last line there. I don't know why I have that many lines, but that's good enough. All right, so x is 1/4, and then we have y is 1. So 1/4, 1. And then we have x is a half. So that's going to be a half. So that's somewhere here. And then we have 1, 0. So 1, 0. And then we have 2 for x, and then we're going to go -1/2, so it's somewhere about there. And then we have 4, and that's going to be a -1, so it's about there. And so what we have is we have this thing. It looks something like that. Okay, and so it's decreasing as it goes down. And that's how it would look. Now, being decreasing, that's what we'd expect if we see, our a is between 0 and 1, okay? And we had 1/4, so we would expect it to be decreasing. All right, what about the 4? Well, again, we're going to take 4 to the y equals t. And so what values are we going to use again? Well, let's plug in, I don't know, 1, 1/2, 0, and then let's go back the other way. Okay, and again, like I said, I don't know why I had so many on the last one. I just counted wrong. So if we plug in 1 here, 4 to the 1 is 4. 1/2, 4 to the 1/2, that's the square of that, so that's 2. What about 0? Well, that's just going to be a 1. And what if, oh wait, yeah, that's square. And if we take the square root of this one, and so it'll be 4 to the negative 1/2. So it's going to be 1 over 4. And we want the square root of that. So it's going to be 1/2. And then if we take, that's a negative. I don't know where that went. A negative 1. So it's going to be 1 over 4. Okay. So what do we get here? Let's see. T. Now this time this is T, and this is your K of T. So if we have T is 4, we get 1. If we have 2, we get a half. And 0 is going to be at 1. And then at a negative 1/2 is going to be a half. So it's going to be something like that. And then a quarter is going to be a negative 1. And so what happens is we have this nice upward trend going like that. Okay. And again, we would expect that because here a is greater than, and so it's going to be an increasing function, and so that's kind of the direction it should take. All right, what about if we do ln of x? Okay, well remember ln of x is equal to log base e of x. So we're going to have e to the y is equal to, and then we just have the x. Okay, now here we're going to have to use a calculator and get our values. And so let's say we do, we could do this 2 different ways. We could actually just plug in values for x here and then get out our ln pretty easy. We just plug it into our calculator. So let's say, we've been doing, I think there was always, a quarter, there was a half. We did things with 1s. Let's try a 2, maybe, and a 4. I don't know. So now if we take ln of 1/4, ln of 0.25, that's going to give us a negative 1.4. And if we plug in the ln of 0.5, that's going to give us a negative 0.7. ln of 1 is going to give us 0. ln of 2 is going to give us a opposite that one, so it's going to be 0.7, and then it's going to be a 1.4. Okay, so again, we just plugged it into our calculator. So if we wanted to kind of show that, we're just going to go here, we're going to quit, we're just going to take ln, and we had the 1/4, and that was our negative 1.4. We had the ln of the 0.5, that was our negative 0.7, and then we took the ln of 1, and we got 0, and then we took the ln of 2, which is going to be the opposite of that, and ln of 4, and that was the opposite of that as far as signs go. All right, so that was pretty simple. We just plugged those in. And again, I haven't been filling in our column here with the points. I'm just kind of going across and doing it that way. So at x equals 1/4, we're at negative 1.4. So somewhere maybe about there. Then we have 1/2 is going to be somewhere about there. And then at 1, 0, so about there. And then 2.7, I guess that's already there, so that's there. And then 4 is 1.4, so maybe something like that. And again, we get an increasing value, and e again was 2.7, so that's greater than 1, and so we expect it to be increasing like it is here. All right, again, a lot of those can be done just on your calculator, typing in ln of 1, 2, 3, 4, whatever, and then just plotting your points. Well, what we want to do now is solve logarithmic functions by rewriting the logarithmic equation into one exponential form and then simplifying. And so what we're going to do is we're going to take and say 2 to the negative 2 is equal to x. Well, 2 to the negative 2 is the same thing as 1 over 2 squared, and so that gives us x equals 1 over 4. Okay. Oh, what about this one? Well, now we're just going to take 9 to the 4 equals n plus 9. And so n is equal to 9 to the 4th. Now if we subtract 9 from both sides, we get that. And that one we just have to plug in our calculator. And so we get 9 to the 4th minus 9 is equal to 6552. Okay, and so again, it's just a calculator thing. And if you need to see that, basically we're just taking 9, raising it to the power 4, and then remember we have to go back down, then minus 9, and we get our 6552. Okay. What about this one? Here we're going to take 11 to the negative 1 is equal to x plus 5. Well, here if we subtract 5, we have 1 over 11 minus 5 equals x. Well, here we have to get a common denominator. So it's going to be a minus 55 plus 1. So it's going to be a minus 54 over 11 is equal to x. Okay, so we had to get that common denominator and then just subtract our fractions. Here we have 5 to the 4. That's equal to negative 10x plus 4. All right, so what do we want to do? Well, we can say subtract 4, subtract 4. So we have 5 to the 4th minus 4 equals negative 10x. So divide by negative 10. And so x equals, and now what we have to do is just plug all that into our calculator, 5 to the 4th minus 4 over negative 10. And if we do that, we can see that we get the following. Let's say we're going to 5 to the 4, then go down, and then we're going to subtract 4, divide by a negative 10, and we get negative 62.1. Which means that this is actually 621 over 10. That's a negative. And so, we could leave it, as this negative 621 over 10, or if we want it decimal, we could put it that way. It doesn't say which one's more preferred at this point. And so, either one of them should work. That one's, just as a decimal. All right, what do we know about the ones where we don't have anything here? Well, that's just a 10. Remember, it's log base 10 of k equals 2, so that's 10 squared is equal to k. Well, that just says k is equal to 100. Well, now here we have 4 to the 4 is equal to n, and that means n is equal to 16 times 16, which is going to give us 256. Okay. And so that's, those two are the simple ones, just taking the powers and it's already solved for n or k, and all we have to do is plug those values in if we don't know what they are. What about these? These get a little bit more hard because they have different values inside of parentheses. So it's going to be 2 to the 1 is equal to negative 8r. Well, 2 to the 1 is 2. So we divide by negative 8. So r is equal to a negative 2 divided by 8. It's going to be 1 over 4. Okay. What about this one? Here we're back to 11 to the negative 1. So we know that's 1 over 11. So 1 over 11. Now if we subtract 1, that's equal to 10n. Well, common denominator, minus 11 plus 1, so that's going to be minus 10 over 11 equals 10n. Now, instead of dividing by 10, I'm going to multiply by 1/10, just because that's going to be easier when I have fractions over here. And so then I see that 10 cancels that 10, so I have a negative 1 over 11 equals n. And so that was just because I knew when I canceled those, that also canceled like that, and then I have that negative 1 over 11 here. And so that's all I have for this section. Hopefully that will help you.